All right. Let's talk about general relativity. If I have a box here and I shoot a laser across, where will the beam hit on the other side? Well, that all depends upon the acceleration of the box. It doesn't depend upon the velocity, it depends upon the acceleration. So if this thing is in equilibrium, then that laser is going to shoot straight across and hit the other side. Because the whole box is moving at the exact same, in the same direction, at the same speed. And so when it shoots across, it'll be treated as if it is not moving and the rest of the world is. Or the rest of the universe, I guess I should say. However, if accelerating, and that's the word accelerating, then if you shoot that laser across, it's not going to go straight across, but it will hit somewhere down here. So in equilibrium, it's going to hit straight across, and otherwise, it's going to hit down there. So Einstein is in 1905, he comes out with a paper. Actually, he comes out with 4 papers in 1905, 3 of which probably could have gotten a Nobel Prize. One of them is he lays out the foundation of special relativity. One of them he lays out the theoretical foundation of general relativity. And the other one, I believe, was when he showed that comes up with statistical evidence for why atomic theory made sense. And the 4th paper I can never remember. So what he speculates for in terms of general relativity, he said if you have 2 situations and there's no experiment that tell the difference between the 2, then they're identical situations. So if I have a person standing in a box, so closed, you can't see outside, and this box is sitting on top of a world. If that person stands on a scale, and he's at equilibrium with respect to the scale, but if he's standing on the scale is going to basically read a force equal to his mass times the acceleration due to gravity. Now, officially the scale is measuring normal force, not weight, but if he's standing perfectly still, then the normal force and the weight are equal to each other. Refer back to your notes for when we did the force diagrams, introduced them. Now, if you are in a box, standing on a scale, and the box is out in the middle of space, except for the box is accelerating at a rate of the acceleration due to gravity, the scale would read the exact same thing. And what he claims is that in these 2 situations, there's absolutely no experiment that can be done to tell the difference between them. Therefore, if there's no experiment that can tell the difference between them, he claims that they are the same. So in this situation over here, if I shoot a laser light across, then that laser light is actually going to hit below where it is straight across. The beam will not go straight across, even though it'll go in a straight line, but the box moves, sort of goes faster as it's going, it covers more ground. Once the laser has left it, it has no idea that the box has moved, and the laser is going to hit down here. So then he claims, if I shoot a laser light here, it therefore will not go straight across, but will hit below. And so he comes up with speculation that a mass, anything that causes a gravitational force or a gravitational field more generally, is also going to cause space itself to be warped. And so that lays the foundation. 1905 is when he comes out with that. 1915, he eventually, at that point, has figured out the math that go along with it. And so 1915 is generally considered more of the birth of general relativity when the math comes included. In 1918, a couple years after that, a man named Schwarzschild comes along, and while he's recuperating from, I believe, a mustard gas attack, he was fighting on the German side, recuperating from mustard gas, and I assume it was a blowback, that he works through this thing called the Schwarzschild radius, which is basically the minimum radius of a black hole, or the maximum radius of a black hole. And so that is where this series of 3 videos is heading. So the next step, once we've laid the foundation here, is to go to the is to set up, find out escape speed. Actually, I remembered one other thing, and I might splice that before this bit. So if a mass here, like a mass of a planet, causes a warping of space, then we can have something known as gravitational lensing. Which means if I have a really large mass here, so large mass, at least it's a more pronounced effect with a large mass, that if I have a light source over here and the light is now streaming in all directions, so imagine 360 degrees, but since I have a two-dimensional board here, as light comes, it will get warped. So basically, it's like you have things traveling in a straight line. The light thinks it's traveling in a straight line, but if I take, say, this line right here, and we get closer to the camera. So if I had a bug walking along this line right here, it would seem like he's traveling in a straight line. However, if the paper is bent, even though the line was straight according to the piece of paper, it now looks bent relative to other things. So this is sort of a similar analogy to what's going on in space, except it's warping in 3 dimensions instead of just 2 dimensions. So you would have this thing called gravitational lensing, where you have light coming in from behind a source, and then it sort of focuses in on one specific spot. Now, in 1919, there was a solar eclipse full solar eclipse that could be seen somewhere around New Zealand, and a man named Eddington goes down there to observe to see if this happens. And in fact, he did observe it. What it would look like from this point of view, if this is Earth here, and this is our sun, is that it would look like the object is in more than one place. Matter of fact, at this point, there are some photos out there taken from outer space where you do get this smear of light that's traveling sort of around. It's not it's not perfectly lined up, but you do get a smear of light coming from what appears to be a single source because of something incredibly massive in the middle. And this is one of the arguments for dark matter, is the fact that there's something there that we cannot see that is causing this gravitational lensing. But anyway, Eddington comes down there during the solar eclipse because that way you block out most of the light from the sun, and what you see is the stuff on the outside, and he saw it. Now on the way back after this, he was asked, by a reporter, "I understand you're one of 3 people who understand general relativity," and Eddington replied, "Oh, who's the third?" So at least he acknowledged that someone else, presumably Einstein, understood it. However, he was not willing to let a third person in on that party yet. All right, so now we will do the foundation, we'll do escape speed, and then that will lead into black holes.